This is our 22nd meeting, and today we are assembled here to discuss about the first assignment, which actually has two parts. In the first part, you are asked to obtain an optimized three-stage Runge-Kutta scheme for an autonomous system for the solution of the ordinary differential equation as given by equation 1. Please note that autonomous equation implies that the right hand side of 1 is not an explicit function of time. That is the definition of autonomous system. Now, in the second part, we wanted to use the optimized RK3 scheme that you have obtained in the first part to solve the following differential equation. This differential equation, as you notice, has a small parameter epsilon, whose value is given as 0.001, and this small parameter multiplies the highest derivative y double prime in this equation. So, you can anticipate that this is going to be one of the traditional boundary layer equation, and you have to solve this subject to the boundary condition given below, that is y at t equal to 0 is 0 and y at t equal to 1 is equal to 1. So, having obtained this numerical solution, you should be able to compare it with the exact solution. We have already indicated that the exact solution of equation 2 is given as the quotient of this two functions, which are essentially the exponential functions involving which we have indicated in terms of x, but please do understand this x and t are synonymous here, and the Runge-Kutta method that you are trying to use here given by equation 1 involves calculating three slopes. The slope at the beginning point u n given by k 1, the first relation, then you would get a second slope which is evaluated at u n plus a fraction of k 1, and finally, the third slope k 3 is obtained somewhere which is different from u n by the two quantities given in terms of a 31 k 1 and a 32 k 2. Having obtained these three slopes k 1, k 2 and k 3, we define the general Runge-Kutta three-stage method as given by equation A, that is u at the new time level is equal to u at the old time level plus the weighted average of all these three calculated slopes k 1, k 2 and k 3. So, the usual way in defining this problem, as we have discussed in the prior lectures, is to basically obtain these parameters of this RK3 method, which involves finding out those three aij's. In this case, they are a21, a31 and a32, plus those three weights that we have indicated as w1, w2 and w3. Having obtained the expression for k 2 and k 3, we can actually expand it in terms of a series as given here as k 2 is equal to h f plus h square a 21 f f u, then h 3 square by factorial 2 a 21 square f square f u u, and h 4 by 3 factorial a 21 cube times f cube times the third partial derivative of f with respect to u. Please understand that since we are interested in a third order method, we retain term up to h 4 to get the truncation error term, which is going to be proportional to h 4. The same way, you can expand k 3 in terms of the function f at the starting gate plus this various functions and its partial derivatives with respect to u at different points, which involves all these unknown coefficients A31, A32, etc., etc. Again, this we indicate all the way up to h cube term. Now, what we have noted that that we could also write down the Taylor series at the new time level T n plus 1 in terms of u T n plus this other terms indicated here. If we equate this Taylor series here with the term given here as A, then we would be able to equate the coefficients of various terms involving powers of h. For example, if we equate the coefficients of terms proportional to h, then the Runge-Kutta method will give you W 1 plus W 2 plus W 3, while the Taylor series will just indicate that is just function is coefficient is 1. The same way for order h square term, we get the equation 2 here, and for the order h cube term, we will have two sets of terms. One will be multiplied by f u square, and another would be multiplying f square times f u u, and when you equate those coefficients, you get these two relations, which are given by 3 and 4. So, basically what we note that we have 6 unknowns, and we have generated 4 equations that allows us choosing any 2 of them. Those are your degrees of freedom. In the following, I am just indicating one way of doing it, that you choose 2 of the w i's. Once you do that, then from equation 1, the third w I is obtained, and you can solve for those a I j's. And in the traditional RK3 method, these parameters are given by A21 as half, A31 as minus 1, and A32 is equal to 2. What we have gone through this exercise, we have performed an optimization and looking at the next higher order truncation term, and that we try to solve, and we obtain the following 2 sets, set 1 and set 2. So, essentially this is what our solution methodology is going to be defined by. So, we can choose any one of the methods and obtain the solution, and that is what rest of you, some of you are going to make a presentation. Let us all sit back and listen to the talk. Aditya, would you please come?
Okay. Good morning, everyone. I'll like to go through a summary of my key observations, which I had during the solution of assignment 1. Firstly, when you solve the set of equations, you get 4 equations from equating the orders of h, h square, and h cube, and you have 6 unknowns, which are on the left panel, W1 to W3 and A21, A31, and A32, and therefore the system is not closed. And to uniquely solve for all these unknowns, we require 2 more equations. So these 2 equations were obtained from optimizing the truncation error. What I mean by optimizing the truncation error is writing truncation error in terms of 3 parts, wherein one of them is a constant, which doesn't have any variables, W1 to W3 or A21 to A32, and the other 2 terms have are some functions of these 6 variables. So basically what we do is we equate those 2 terms to 0, and therefore the system is now closed and we can uniquely solve for these. It turns out that when you do that, you end up with 2 sets of solutions, which are your optimized solutions, which are shown in the first and the second column. It's quite surprising that values of these constants are so far from each other. I mean, you can, if you look at the first and second panel and compare it to the standard RK3, which I got from hopefully some reliable sources, it's quite clear that they're very different with respect to each other, in that if you look at A21, it's equal to 1 in the set 1 and equal to 1 by 3 in set 2, which means that if you look at set 1, what it does is it shoots across the entire step size and goes to the next point and then calculates the slope. Whereas in the second method, what it does is it goes to 1/3 and then goes to minus 5 by 12, which means it goes in the opposite direction, and then goes plus 5 by 4h, which means it shoots to more than h to come back to the third point. So basically, both these sets of solutions are very different from each other in their characteristics. So we look at, this is the question I asked here, is which of the two optimized solutions are more accurate, if at all. So what I've done here is I've plotted the absolute value of the difference of yn1 and yn2, where yn1 is the numerical solution obtained from the first set of solution, that is w1 equals 1/6 and so on, and yn2 is the numerical solution obtained from the second set of constants, which is 1 by 10, 1 by 2, 2 by 5 and so on. And I plot that as a function of t, which is the independent variable. And this plot which I've done is for a step size of 10 power minus 4, which means I've taken 10,000 steps and I've seen how the absolute value of the error between the two optimized solutions, the two numerically optimized solutions, varies with the independent variable. And if you look at the order on the y-axis, it's of the order of 10 power minus 16. It doesn't have a unique value. It ranges between 6 into 10 power minus 16 to around 11 into 10 power minus 16. Now it might seem that one method is therefore more accurate than the other, but keep in mind that we are doing a numerical computation, and therefore this 10 power minus 16 is basically the machine epsilon. It is nothing but it's nothing but a machine error. The machine cannot do a calculation, cannot represent something more precisely as 10 power minus 16, and therefore I believe that these two solutions are as accurate as each other to within machine precision. So this is clear. So what I've done here is I've plotted, so now that we know that both the numerical solutions are as accurate as each other to within machine precision, I just take one of the two sets. I think this one I've done for a21 equals 1 by 3, that particular set, and see how that compares with the exact solution, and done that for a range of step sizes. We expect that as you increase the step size, at one particular step size, the solution stops converging to the exact solution and shows large deviations from it. And that's exactly what we see. The first four plots are, as you can see, the first one is for h equals 800 inverse, 600 inverse, 550 inverse, and 500 inverse. You can easily compare the numerical and exact solutions. If you look at 800 inverse, the numerical solution and the exact solution are indistinguishable from each other. Whereas at 600 inverse, you can easily see that there is a red spike that is sort of deviating from the black curve. The red one is the numerical solution and the black one is the exact solution. And as you increase h more and more, you can see that the error between the numerical solution and the exact solution keeps on increasing, which is what we expect. These four plots are essentially the key plots for 475 inverse, 450 inverse, 425 inverse, and 400 inverse, which shows very clearly that the deviation of the numerical solution from the exact solution, it really increases very rapidly as you increase the step size, and the program stops to terminate above a value of h equals 400 inverse or around 395 inverse, which means that is the critical step size above which you cannot, that is the maximum step size that you can take for to have a stable solution, although not very accurate even at 400 inverse. So it may not be very clear what the exact value of the so-called critical step sizes from these plots, because they're taken at few values of h. So what I've done here is I've plotted the root mean square deviation of the numerical solution from the exact solution. How I do this, I've shown it in the top left insert in the plot. I define the RMS error as that, which means there yn at xi plus kh minus ye at xi plus kh. That difference, the whole square, and I summate that over all the steps and divide by number of steps and take the square root. That's exactly how we define the RMS error. And the reason I take the RMS error and not just the difference of yn and ye is because of this. As you can see, for example, in h equals 400 inverse, the difference between the numerical and exact solution is positive, and then becomes negative, positive, negative, etc. So it makes more sense to define the error or the deviation of the numerical solution from the exact solution in this particular way. So this is what I've done, and there yn is the numerical solution. Again, like I said, I've just taken one of the two numerical solutions because I've shown them to be as accurate as each other to within machine precision. So yn is a numerical solution and ye is the exact solution which I have derived analytically. xi is 0 in our case. It is the initial point of our x interval. Probably that should be ti because I've defined ti as the independent variable earlier. I'm sorry about that. And k is the index of summation and h is the step size, which is 1 over n in this case because it is xf minus xi divided by n. So basically that is my RMS error, and I plot that as a function of step size. And as we expect, the RMS error or the deviation of numerical from exact solution increases. It's very, very small for the values of h around up till about 10 power minus 3, which is 0.001 on the x-axis. But beyond that, it starts to rapidly increase, and you can see that for h equals 400 inverse or 0.0025, and for values of h more than that, the RMS error is really, really high, which means that can be sort of defined as a critical step size. Of course, critical doesn't mean that all step sizes up to that will give you sensible numerical solutions. As we have seen, h equal to 400 inverse gives us pretty trashy numerical data. So it would be advisable to stick to the range of the tiniest RMS error on that graph. I'm just trying to show, I mean, this makes sense because if you look at the nature of the exact solution above a particular step size, I mean, there's a very sharp variation of the exact solution at the peak. Right, around less than 0.01, there's a peak in the exact solution. So whenever the exact solution varies very rapidly, there's a good chance that the numerical one deviates from the exact one. As you can very clearly see there, it starts to deviate exactly at the peak. So for such functions, for such exact solutions which show very sharp corner or very sharp peak in their graphs, we would really expect that above a particular step size, the numerical one does not converge to the exact solution at all, which is exactly what we see here in terms of the RMS error becoming very, very high, above h equals 400 inverse. So that is basically a summary of my results. Anybody would ask?
Yeah, I think we are now open for discussion, right? Let's open it to the floor. Anyone having any observations?
Go back to the slide. I mean, second last or third last slide, where you were showing the numerical and the exact solution graph.
This one?
No, after this, yeah, for 400 inverse.
Yeah.
What is that graph? What is it showing exactly?
Oh, no. Okay,
400
so
inverse, yes.
yeah, for 400 inverse, this is the exact solution. In all other cases, this is the exact solution. Maybe I should have indicated with an arrow or something. So this is the exact solution. This is a numerical solution. So I don't know why you're having two bands if that's your question.
Yeah.
Probably you have 3 points that define this peak. You have 2 of them here and 1 on top. So it sort of looks like a triangular thing. I mean, that is an artifact of, I don't think there's anything to do, I mean, I don't think the 2 bands exactly have any meaning.
It does.
Do they?
It does, right?
What do they mean?
Utkarsh, what does it imply?
It's that the first band is like most of the time you get that, and but at a particular time means for a particular x that you go to the higher band.
Well, I'll interpret what he is trying to say is you take a FFT and you will see there are 2 dominant frequencies. One corresponds to rapid variation, that corresponds to the denser lines, and one is a little, yeah. So it's a very easy thing to do. For one to do is basically take a FFT. You're seeing it's an oscillatory solution, you know. That's a harbinger of any instability. It always starts off with some kind of instability and then it goes beyond control. But one thing while explaining about RMS error, you made the observation that the excursion could be plus or minus, but as you can see in your case, it was always positive. So it wasn't a
no, yn minus ye can either be plus or minus.
Yeah, right, right.
That's
So you could have taken the norm, I mean
I
just
could
the
have taken
absolute
the
value.
value as well.
Yeah.
That's right.
So that is what is called as L infinity. Okay. What you have done is you have shown L2 norm. Any other questions?
I was just
Find out what would be the value of h. How we can get the value of h? At least the
Well, you have an estimate for your error, you can take a look at it, but again you did not show the expression of truncation error, but if you would have looked at the expression for the truncation error, you want to, if you want to take a look at your, yeah, you could use your notes and yeah, and if you could write it down, you would note that the truncation error has two components. One depends on the parameter of the method, another path which is independent of it. So in that sense, this is not really absolute optimum, because yeah, Jishnu.
So what is happening is you have to solve getting 6 unknowns to third order, out of which 4 come from the basic condition, the equity.
Mhm.
6th one comes from the truncation error. The 6th one is still arbitrary.
No, that's what. Please hold on, let him finish writing. You will see he get both the 5th and 6th from the truncation error expression only. That is H4. And yeah, you can see that he is writing the leading term is order H4. Well, while he writes, the rest of you can continue the discussion. Yeah.
The number of, I think it depends on the number of truncation terms you take. We just take the leading term.
Yeah, so it's always like that. That's the way you define truncation error, is the next neglected set of terms. So what he has done here, you can already see there are two sets of terms which depend on this coefficients, right, W1, W2, W3 and A21, A31, A32. So those are those two sets. So what I suppose most of you have done is put this equal to 0, right. That is one way of doing, right. Is there any other way we could have done it? Yes, Shakti?
Take the
Set it the differentiation of what?
first use
This error with respect to?
W2 or W3. What's the difference?
Right. So that's another way of doing it is you convert those 4 equations into a 2-parameter family of solutions, right. So arbitrarily choose. Well, it's probably if you plot the truncation error term with the variation of these coefficients, it probably has a global minima there with respect to those 2 terms, right. But there could be a third alternative. I would leave that towards the end, so let other people can also get in and okay. So we'll thank Aditya. Yeah.
He has also got the second set of those values for W1, W2.
Yeah.
How did he get those two?
Well, it's a actually it turns out to be a quadratic in some of the
I
parameters.
reduced everything to quadratic in A21 and I got therefore 2 values of A21. One
In fact, I think you got 3, right, Sonam?
One was inconsistent.
Well, how do you say it's inconsistent?
It was 0. One
So why should that rule it out? If W3 is 0, that's fine. I would require less computation.
can't be because
because the
now
equation W3 into 2 variables is 1.
Okay, so one of the conditions should be violated. Okay, that's fine. Okay, okay. Thank you, Aditya. we should now move on to the next one. Okay, Mohit and Himanshu. Yeah, you have the microphone and the chalk. You can probably, it's good to keep this expression in front. Yeah, bottom, and the bottom left there is a cup. Click on that. The third, no, yeah, that's it.
Good morning everyone. Well, the problem that we had was we had a second order differential equation with boundary values, and we had to find we had actually to optimize the RK3 method for the computation of for the numerical solution at various values of t. Now again, while solving the equations, we get three set of solutions. Well, in one of which a21 comes out to be 2 by 3. When you put a21 equal to 2 by 3, then by the other equations you find that the system becomes inconsistent. So that value can be neglected. The other two sets have been shown here, where a21 is the one that has been neglected was a21 is equal to 2 by 3. In these sets, in one of them a21 is equal to 1 by 3, and in other one a21 is equal to 1, and these are the solution that Aditya pointed out. Next, if we plot the exact solution, it looks like this value. So we can clearly see that it's actually a boundary value problem. The gradient here is very sharp. It shoots up to a value of 2.6 in a very small interval, and then it decays very gradually. So it's actually a boundary value problem, and so we can say that the equation is a stiff equation, and the value of the step size would determine the nature of the solution that we are actually getting. Like we said, we get the two solution sets. So while comparing the two solution sets, this is the plot of the numerical error. The red one shows the numerical error and the numerical solution, and the blue is the exact solution that we have plotted using the code in C. So this is the kind of plot that we get. This is the exact solution, this is the numerical solution. So we can see some kind of wiggling here, as Aditya also pointed out, at h equal to very large value, it's 500 inverse. So this is some kind of wiggling here. We can see similar kind of wiggling in the second solution set. As we decrease h value, it's 1 by 1000, so the wiggling decreases. But still the solution is not exactly correct, because this is the region of where the solution differs. As we still increase h, the solution almost overlaps with the exact solution, and it happens in both the solution sets. So we can say that both solution sets are almost identical. Now, since both the solution sets are almost identical, so we take one of them and we show the magnified view. Now this previous slide, so this was a region where of consideration where we were showing some kind of wiggling. So now we'll magnify that thing. Yeah. So in this, the value of h is 500 inverse, and blue is the exact solution. The red one is the numerical solution. So this is this kind of oscillation we get. As we decrease the h value, there is some difference still present in this interval. We again decrease it. Again, we can see some very fine difference between the two sets. Like the blue is above the red one, but as h decreases further, these two solutions almost overlap. So we can see that there is some value of h, optimum value of h, below which the solution would be this good, and above which, like somewhere around 10 to the power minus 3. If the value of h that we take is greater than 10 to the power minus 3, then the solution that we get is not exactly a correct one. These were the relative RMS error. Now, how we calculate the relative RMS error?
Is it any different than what Aditya did?
At
t equal to 0 we do not take because that is the point.
Well, that is anyway 0
Yeah.
anyway.
The
It
same,
doesn't contribute.
Aditya
It doesn't
showed.
contribute.
So this is the relative errors that we get from solution set 1 and solution set 2. Again, it depends upon the accuracy of the machine that we are using. So for h equal to 500 inverse, this was the error for set 1 and set 2. We can see that these figures are same. What differs is these values. Similarly for the various values of h, so these figures are same.
It's okay. Don't.
We're only
there's-
differing in the last values. And when we actually try to look what is the order of this error, the difference in this and that, it actually comes out around 10 minus 14 for some and 10 minus 15 for some.
So did you do a double precision calculation or single?
Did a double precision calculation, and this shows that it's not only the machine error, there is a little bit of difference in the two solutions.
Well,
Till here the solutions are same till this figure, but then they start.
And that's also 10 to the power minus 8, so that's 10 to the power minus 15 precision. The two errors are same up to 10 to the power minus 15.
can you make a guess why it could be?
So,
Anyone in the class?
So again, that depends upon the.
Probably the difference is coming because we are taking minimizing the truncation term. So up to this order of magnitude, the truncation term does still coming, which is why the effect comes after it is about.
So I mean, what are we saying?
No, but this is we have done the similar kind of truncation or a minimization, truncation and a minimization for both the sets. We minimize the truncation error and
Becomes prominent. The order of magnitude of the other quantity is such that the truncation error becomes prominent only after the 15th decimal place or something.
No. It is happening much before. If you look at the 50,000 data, I think it's in
minus
the
8 also.
the 7th or 8th decimal. My question is why they are different.
So that's 10 to the
So
power
10
minus
minus
8.
8.
That's also 10 to the power minus 15.
Doesn't matter. That's my see. When we talk about rounding off, we talk about significant figure, not the exponent. Keep the exponent out of the picture. Okay. So that's where you are still in a single precision domain. 10 to the power minus 8. It's not in double precision. You should be able to get up to 10 to the power minus 14. So my question to you, all of you, to think, because Aditya also mentioned machine epsilon. What is machine epsilon? You have done 2 courses, some of you, but all of you have done the first course on computing, right? So what is machine epsilon? What is this? What animal is this? Shall we have someone else to answer? Yeah, someone, Mansi was trying to say something. Yeah.
Machine epsilon is the error is arriving to the computation by limit of the machine. It's error due to the machine. It is nothing.
So what is this error due to machine?
So if a number can be represented exactly in the binary format, then it's
Well, the smallest number which can be represented by the machine, it's the double can be represented, since double has a precision of 8.
So is this some kind of a sort of a barrier for a machine?
Yes,
Or,
Sir, it cannot.
are we saying that we cannot represent a
Any language, let's say double a comma b,
Uh-huh.
then we write if a equal to b, it means if mod of a minus b is less than epsilon, then the machine.
So basically I'm asking, throwing back the question at you, are we saying there is a Lakshman Rekha beyond which we cannot do given a machine?
That depends on the register size. I mean, a 64-bit machine can only have a certain number of digits.
That is not correct. That is not correct. Have you heard of long double, quadruple precision? You can define and you can store the numbers. So what happens is the same number.
You can define a user-defined data type. You can just keep on
No, please try to understand what is actually done when you store a number, a real number. You assign some storage space for each significant digits, right. Single precision you would be talking about 7 digits, let us say, for some particular hardware. Double precision could be, let us say, 14 digits. Long double, it could be 18 digit, it could be 21 digit. So what happens when I am defining a quantity, a double precision, what I am doing? For each number, actually I am allocating 2 spaces, right. So I could do much more, I could do define quadruple precision. So there is no such thing as machine epsilon, right. So it is something which depends on our ability or our desire to express a number. We can do it, but at the cost of more memory and more computing time. And the thing that we are talking about, having decided upon the significant digit you want to represent, so you are basically rounding the number off beyond those digits. So this would be a better term to call it a round off error. Okay. So you can have a different kind of round off error for different declaration of precision. I am sure it must have been taught in your first course in computing. Okay, you made a mention that you have done some calculation, these are coded in C. Did you did Java?
Yes, Java.
Okay. Is there anyone who may have tried to do it in 2 different languages and seen if, yeah, of course you did. What about the speed? Did you see any? No? No difference? Maybe this problem is too small?
So C is always faster than Java.
So we have different results. Our code is, our logic is
Identical, yeah.
I did it in Java, she has done it in MATLAB, and we are getting different results. We are not getting the magnitude of error is different. Magnitude of error is different, and in certain cases are.
So we still haven't answered that question. Why those 2 last entries are different in the 7th or 8th decimal place when the calculations are done in double precision? Why would they be different? Because as you can see, we have identical prescription, right, up to H4.
Maybe there are different in step sizes. Like in the first.
Both are same step size.
No, not the step. I mean, when you are taking A21 value.
Uh-huh.
In one case we have value equal to 1, whereas in the other we have 1 value. So
No, but at the same time your error is uniquely defined. In both the cases those 2 terms have been, see, that is why I am not surprised that those 2 sets of results are almost identical. I am asking you a throwback question, why it is almost and not exactly? The answer must be staring at your face. Anyone?
So,
But that is probably, I mean, that is where when the machine is calculating, it is rounding off at that stage.
Are you attributing it to round off error then again? No, we do not agree.
there might be one more reason. Since we are using the shooting method, right? So, okay, the error is the error might be 0 for a same value. If it is the same value of initial z prime, then the error should be the same, right? But when we are doing it by shooting a method, we are not exactly saying that they are converging to the same value in the same fashion.
Okay, I think we will go to the next presentation and then towards the end I will come back to it. I think we will go to the next. Yeah,
This is the
this is the,
plot of the
yeah.
relative RMS with the edge as
You know, Mohit, I would suggest to all of you, whenever you are looking at error like this, please use log scale, otherwise you are not seeing the, you are not able to distinguish between different cases. Okay. Okay, I think, yeah.
when you feel that
Uh-huh.
a more efficient method could have been like which said that in the region of t equal to 0 to 0.02.03, that is the region of the consideration where the gradient is very large. But if we take h to be uniform, like very small for the higher values of t also, then actually we are wasting the computational resources. So an efficient method would have been to take the sufficiently small value of t for smaller values of sufficiently small values of h for t small, and as t increases, since the gradient is not that sharp, so we can even increase the h value. So that would have given.
So we are all lazy. We didn't think and reduce our work. You did?
Basic question here. So whenever we are doing the transition error minimization, we are going through all this algebra. What I did was I checked by using the traditional coefficient.
Well, I don't believe what is traditional.
No, sir, let's say,
Are we too modern?
no, sir, answer. My question is taking any arbitrary coefficient
Yeah.
and taking the optimal coefficient, the amount by which it improves the error
Uh-huh.
is much lesser than doing decreasing the step time.
Has anyone obtained the solution with standard method and compared the error? You did. Okay. So I think we'll come. Why don't you just come in and we'll go to the next.
Most of the things have already been discussed, obtaining how to obtain the exact solution, the numerical solution, all those things. These are the parameters which we worked upon. Yeah, you can't hear.
Okay, so this was how we moved on. We had to assume certain value for y prime at x equal to 0 in order to march ahead to compute the solution numerically. So we employed the grid search method in which we we restricted a particular domain for y prime equal to 0, that is from 1 to 3000. Because this domain we chose because if you go for the exact solution, you will get y prime 0 to be around 2715, some value like that. So that is why we chose our domain to be like this, and for every value of y prime we obtained the value of y at x equal to 1, and that shooting method, you will see if it matches, then it's better, otherwise we again go to the next value. We obtained values of y at x equal to 1 for all the values of y prime at x equal to 0, and we plotted it. This is the plot for y at x equal to 1 versus y prime at x equal to 0. You can see if we want to have the given the boundary condition at y at x equal to 1, which is equal to 1. So for that value, if we interpolate it, we'll get some value. Numerically, we get. I have got the value of 2684, which is quite close to that value. So for that value, this is the plot for the numerical versus the exact solution for 2684. This line shows the numerical solution, while this dotted line, if you can see, shows the exact solution. So there is some difference between the exact and numerical solution, and if that difference, what has been done here, that is the root mean square of that error, that's the difference between the exact and the numerical solution. If we plot it, we'll get something for and this is error per n versus n. That is, n is the number of grids that we employ, and versus n. So this is how we get. Now, and one important thing using this graph is we can use this graph in order to determine what should be our number of grid points to be employed, or rather what should be our grid size. As you can see that as we go on increasing the number of grid points, the error per n decreases, and so this can give us an estimate of how many grid points we can employ in order to get as close to the exact solution as possible.
That is provided you take h as same.
Yeah.
That's very
Provided h.
provided space is same.
Spacing is uniform.
So I mean, based on what we just now heard, that would be probably a good idea to keep it in the inner part of the boundary layer.
Yes, sir.
In the outer part, we could be a little more liberal, right?
Yeah, exactly.
And probably even that 400 limit is not a correct limit. If I were to do it, I would get the solution in 200 points by having variable space. Yeah. So that's how it should be.
So if we consider this is the form of solution which we are getting. So this is quite like a boundary value problem. So what we are talking about is if we divide this domain, this whole graph into two parts, we can solve for this domain, we can have a different grid system, and for this domain we can have a different grid system. For this, since the change is quite gradual, we can have like the grid spacing could be not that like refined as for this case. So like we can have a non-uniform grid system in order to solve this problem. That could be much faster than like having a uniform grid system and like a refined grid spacing for the entire range.
Coming to the conclusion part, it is clear, it is quite clear from the graph that as we keep on increasing the number of points, our error keeps on reducing. The most important thing to note about the equation was that it was a stiff differential equation, and stiffness ratio was quite high, it was quite close to 1000, it was 1000. So
that is epsilon, actually 1 over epsilon.
It is 1000, so the grid size will matter most. One more important thing, we'll observe that our solution is two parts. So if we take the, as sir said, if we take the fast Fourier transformation, there will be two frequencies dominating, like he showed for the two modes. So the analytical solution explains that part also.
Right.
So we also took some smaller values of the grid for which the solution diverges very rapidly. So that also puts a limitation of the step size. And I thank you.
Okay, so now, yes, I think now we missed one of the presentation. We'll do it the next class, right? You would get a proper, yeah.
The first graph.
In this case, yeah, let me first graph, okay.
So is it necessary that it is always monotonically increasing that?
Now, what is the question?
He's saying like the graph is
Monotonic.
So is it necessary that it has to be?
It doesn't have to be. So, see, the point is what they have done is what is called as a grid search method. You identify a parameter space which is defined by y at x plus 1 and y prime, and then you keep on doing it, and then the moment you find out where your far field condition is satisfied there, you keep zooming in that area and take much more refined grid search. And this method may appear to be more compute intensive, but there is a beauty to this method is that sometimes you may have multiple values at the wall that could satisfy the far field condition. So, if you are doing shooting method, you always get only one of it. So, you do not get the whole complement of values which can satisfy the far field condition. So, in the grid search method, you would get the whole set of it. So, that is something that we could do.
Suppose we have a higher value of y prime, which is also satisfying the grid.
Yeah, right.
We are losing that value by grid search method, right?
No, you will not. That is what we are saying, that you have to have enough range, It is almost like your bisecting method, you know, I mean, yeah.
The bisection method, if we come close and then make our epsilon smaller.
Smaller.
then grid search.
So, it is exactly the same. It is not anything esoteric than that. Okay. So, I suppose the only thing that we did not hear is anyone doing variable h calculation. But you see why I am saying this, because if you now happen to go to any of those canned programs, solvers, what they have actually, they decide upon the step size by local truncation error analysis. So, at each and every point you go there, you find out what is the optimum h for that particular step. So, it is not like what Shakti said, that for the inner layer you take one step size and outer one. It is not necessary, because your method does not depend upon the fact that you will have to have uniform spacing. You can give any spacing at any point in time, right. So, that you could do. Okay. The only question that I wanted to answer was what Himanshu and Mohit showed, that even with 50,000 points, there were some discrepancy on the 7th and 8th percent. The answer is very simple, because all that you are doing, you are equating up to here. what happens to the next order? Once you have exhausted this, the next one will play the role of leading error, right. So, that is where the difference comes in, right. So, that is where the difference would be. So, there are no mysteries, right. Are there any? If there are none, so I suppose we now understand certain things. I did not discuss about various sources of error, but we have talked about one thing quite a bit, is the truncation error. Today we did talk about round off error, and unfortunately this round off error does not get its due attention, but it could be a very significant issue, especially when you are solving problems which are physically unstable. When a problem is physically unstable as opposed to numerical instability, those physical instabilities are triggered by some background disturbances, right. That is where the noise environment plays the role in a computed solution. So, that is where the round off error does play a significant role, but it has not been very much well probed and analyzed, but slowly people are becoming aware of it lots of the time. For example, we do some of this kind of work where we find out that an aircraft is flying at an altitude of 11 kilometer, what kind of background disturbances we have and how does it affect the flow field. This kind of analysis is attempted, and when we do that we realize that round off error actually plays a major role. So, what happens is there are all kinds of strange prescriptions suggested. Few years ago I heard French scientist actually took a patent for controlling round off error, and which turned out to be total nonsense later. So, this round off error is quite a significant parameter to consider to be important when you are looking at the mean field, like equilibrium solution like this we are getting. See, this is your equilibrium solution, right. The boundary layer you have observed, it is the equilibrium solution. Now, what one could do is perturb this equilibrium solution and see if those perturbations decay or amplify. That is how we do physical instability studies. So, the perturbation field does play a great role, and that is where we should be paying particular attention to this. The one more thing that I wanted to tell you is about this optima that we have seen, couple of them. That still does not factor in one aspect. How does the error depend on f? We have been totally silent, right. We have been playing around with the coefficients of the RK3 parameter, and we are talking about how to minimize, make this two component 0, but still this remains, right. Suppose I give you a problem where f is defined, right. I could do that. For example, this is what you can think of negotiating in near future, that this is what we keep talking about. So, if I look at it, I could write it like this. So, this could be a f, right. That could be the f that we need to solve for this particular problem. Then what happens? Then you should then minimize the error, not only these two terms, but all the three terms taken together. That would be a much more of a global search, right, global minimum. And well, as you can see, it is coming your way on as the third assignment you would like to do. So, you can actually build up on your knowledge what you have done on first assignment, use it on the third, and come back and share your experience. So, we will do that, we will do that. So, that is something it's something we have done. Now, another aspect of optimization that we talked about, it is sort of a lopsided approach, because we kept our attention focused only on truncation error, right. Is that the only source of error apart from truncation and round off? We have already seen in our error analysis part of the discussion. There are physical sources of error which relates to, we have seen numerical instability, numerical stability also can cause error. We have seen if there are convective solutions, if they are going at the right speed, right, the group velocity is a major parameter, dispersion. So, you can see there are other aspects of optimization. I probably have mentioned to some of you. We do some such work. One of our PhD student is actually developing a RK3 scheme. It's a PhD program. So, what you people are doing, it's not trivial. Okay? So, people do look at a corresponding thing, but there we look at all those physical mechanisms, how to minimize those kind of errors. So, if we have a wave propagation problem, how do we minimize the error there? So, that is also something that we can do. So, it's good. I suppose now with this exercise all of you understand that how one does research. It is not always something that you reproduce what is already there in the textbook. There are issues like, as I said, George Orwell's quotation, issues within issues. So, people when you go deeper into it, then you see there are lots of other aspects emerging, right. I think we had a very fruitful discussion today. Unfortunately missed one, but we will catch up with it. And any of you, rest of you, if you want to come up or discuss, please do it either on the podium or we can do it through the email, right. We have a course ID, we can bounce off ideas from on each other, and I did not want to have this chat group or something. I think that ends up becoming chat. It's better to keep away from all this fancy things. Well, I think with this I would now say that we are mostly done. If any of you have any questions about this or anything else, feel free to discuss. We have well, another 4 or 5 minutes to discuss if you want to.
So in the last presentation they started error by n versus n, which can be misleading because the error can be a constant and as you keep increasing the number of n.
Which one are you talking about? Elliptic?
In the last presentation.
Oh, that Shakti's presentation.
Yes.
Okay, let me. Yeah, what is your point, Manish?
What's the rationale behind starting error by n versus n?
This one? Yes. So, it is basically a sort of average error integrated over the domain. You have added the error for all the n points and then.
Would error versus n be a better measure of this? Because this can be misleading.
This is always, well, that is why statistics is not pure science. When you average out, you can put your hand in a hot stove and a chiller tap and you can say you are having a normal experience. It isn't true, right. So, that is a problem with always statistics. So, be very cautious when you deal with statistics. Do you know that there are, on a lighter note, we have some time to talk about. People have found out a very strong correlation with baldness with Medicaid support in USA. So, of course, the people who are bald, they are older and they also go to the doctor, but is that a good correlation to draw, right. So, I suppose statistics can be very, very misleading. So, error, of course, it obscures. Whenever you talk about averages, you are talking about only one statistics. What about the higher order statistics? So, RMS error is 1, that is the second order statistics, right. Well, if you are fancy, you can go to kurtosis, skewness, all kinds of things, third order, fourth order statistics and find out.
Sir, in the transition error, we said there are 3 methods of actually minimizing the error. So, one is equating the coefficient to 0, other is the differentiation. What is the third one that you were saying?
No, I said that if f is prescribed, then I could do a global search. And I did not say 3, I did add few more, that if we are interested in optimizing certain aspects of error, like that is what we did, we corrected the von Neumann analysis from that angle, right. Okay.